Hoover High AP Chemistry, we're continuing with the Day 60 answers video, and we're continuing to do resonance structures and formal charges. Alright, so let's go ahead with C. You saw this one in the instructional video, but go ahead and try to do this on your own. That's the key, is to learn to do these without looking at the answer. So let's draw two possible structures for CO2. Alright, so we have one carbon. Each carbon has 4 valence electrons, 2 oxygens. Each one has 6 valence electrons, so they have a total of 16. So we're going to go ahead and we're going to place the carbon in the middle. It is less electronegative. And we'll go ahead and fill this out. Single bonds here and here create octets around the terminal atoms. Okay, so now we have 8 and 8, we have 16, so we don't want to take away any electrons. We have the correct number of electrons, but carbon doesn't have an octet. So the only way to do that is to rearrange them. So what we've done before is we did this. Okay, and that gives every atom an octet, and it has 16 electrons. However, there's another possible arrangement that you could have done, and it's this one. Okay, so we have 8. We have 8 around carbon. We have 8 around this oxygen. That also meets the requirements. There's 16 electrons used, and each of the elements has an octet. So we're going to use formal charge to analyze each of those. So we'll start over here. Oxygen, you always start off with the number of valence electrons that the element has in its natural state. Line here. And that's 6 for oxygen. Minus how many lone pair? So 1, 2, 3, 4. Minus 1/2 of the bonding. 1, 2, 3, 4. 6 minus 4 is 0. Carbon. 4 valence electrons in its atomic state, minus no lone pair electrons there, minus 1/2 of the bonding. All those 8 electrons are bonding. So 4 minus 4 equals 0. Oxygen on the other side is exactly the same as the oxygen on this side. Okay, so that's extremely stable. Everything's 0. So that will exist in nature. Let's see if this one will too. Maybe they both do. 6 minus 1, 2, 3, 4, 5, 6 lone pair electrons there, minus 1/2 of these two, 1/2 of the bonding, which is 1/2 of 2. That's going to equal -1. So all of a sudden there's a charge on that oxygen that makes it somewhat unstable. Carbon has 4 valence electrons. There are no lone pair in that particular configuration. Minus 1/2 of the bonding. All of these are 8 electrons that carbon has around it are bonding. So it's still stable, even though it looks lopsided. The electrons around carbon, that's still considered stable for carbon. And finally, we have the oxygen on the right. 6 valence, 2 lone pair there on the right. Minus 1/2 of the 6 bonding with the carbon. That gives you a +1 charge. So the charge is balanced in the overall molecule, but it's still drawn to one side. So that is an unstable configuration. So this would be, so this is the stable configuration. That's what would be found in nature, okay? All right, I said earlier in the video, let's talk about what this formula is saying. It's saying that oxygen naturally has 6 valence electrons. That's what it's used to having. So we're going to see how many does it feel like it has in this particular bond right here. How many electrons does that oxygen own? How many belong to it? Well, 1, 2, 3, 4. The lone pair entirely, all the lone pair electrons totally belong to that oxygen. They're not being shared with anything else. So there's 4. And then you just reason that 1/2 of the bonding electrons belong to this oxygen and 1/2 belong to the carbon. So 1/2 of 4 is 2. So that means this oxygen owns 1, 2, 3, 4 plus 2 more of these bonding electrons. That's 6. That's what oxygen is used to feeling in its natural atomic state is 6 electrons, and that's what it feels here. So it's very stable. It likes the way it feels there. Okay, if you came over to this oxygen over here, that's the one on the left here, it's used to having 6 electrons, but it feels 1, 2, 3, 4, 5, 6, plus half of these two, that's one more, 7. So it feels like it has 7 electrons, but it's only used to having 6 in its atomic state. Therefore, it feels like it has a little more negative charge than it should, and that's not stable for oxygen, and it's not stable for the overall molecule, therefore. And that's, again, what's going on with formal charge. All right, let's do the NO2. There is a minus sign there, notice that. So let's go ahead and do that one. And actually, I'm going to scratch that out. That minus sign should not have been there. NO2 is not an ion. Okay, so that's one of the advantages of watching the answers video, is it'll correct little things like that. Yeah, yeah, no, that's fine. All right, so let's go ahead with the oxygen. It's 6E minus, and that's going to give you 16E minus. Okay, let's draw 2 structures for that. And nitrogen is less electronegative than oxygen, so it should go in the center. But let's try both. Let's try this. And let's try this, which looks more balanced, but oxygen is a more electronegative element, so it shouldn't go in the center. Let's say we're not sure which of those 2 configurations. There's no other possibility. If we put the 2 ends over on this side, that's the same as this. So those are our 2 possibilities. Let's see which one works. So we're going to go ahead and put electrons here and here. We have 16 electrons to work with. We're going to create an octet around terminal atoms. And so we have 16 and 16, but nitrogen in the middle does not have an octet. But you have the correct number of electrons, so therefore you don't want to take any away, you just need to move them. So we're going to move these on the outside. Okay, and there, everyone has an octet, we have 16 electrons, so that's all good. Okay, let's try this one. Well, if you look at this, you see you could have formed the same configuration as that. It's just oxygen is in the middle. Okay, that would be the same thing. Let's see. Another thing you could have done is you could have done what we did with CO2 up there. You could have made a triple bond on one side and a single bond on the other. Let's skip that. We're not going to do all the possibilities. What I'd like you to do is just do at least 2 possibilities that meet the rules of a covalent bond, but that are alternate possible structures, and let's do formal charge and see which one is the more stable. So here we go. So nitrogen has 5 valence electrons. This one has 1, 2, 3, 4 lone pair. Minus half of the bonding, that's half of 4. And that's 2, so 5 minus 4 is 1, minus 2 more is -1, so already we have a charge going here. And that still could be the most stable. Just because there is a charge, don't quit. It doesn't mean that that won't be the most stable configuration. It's just, we don't know. Well, we just don't know until we do both. Okay? Then now the nitrogen in the center, also 5 valence electrons naturally, minus, it has no lone pairs, minus half of 4. Half of 8, rather, which is 4. So 5 minus 4 equals +1, okay? And now the oxygen on this side, 6 valence electrons to start with, minus 1, 2, draw them a little darker here, 1, 2, 3, 4 lone pair, minus half of the bonding electrons. There's 4 of those. So it's 6 minus 4 minus 2 is 0. So everything is balanced. -1 + 1, 0 is no charge, and there is no charge because we did take it off there. Okay, so that's one possibility. Let's try this one over here. Now, if this does turn out to be more stable, then it will be an exception to our rule that the least electronegative element goes in the middle. So let's go ahead and do this, nitrogen. And this nitrogen is going to be the same as this one over here, and so is this one. These two are going to be the same as this one over here, but let's just go ahead and write them out. Okay, and you can see these also add up to 0, but there's a lot more charge on this one. So this appears to be a more stable configuration. Maybe what we should do is try one more. Alright, so since we didn't get a 0 in any of these, let's try one more structure here. Let's try one that looks like the carbon dioxide above, which would be this. Okay, again, meets all the rules of a covalent bond. So we're going to start over here. Take a little space away from this one here. Do it over here. Okay, so the first N is going to be 5 minus 6 minus half of 2. It's going to be negative 2. 6 minus 0 minus. So I don't know where I got that from. Moving a little too fast there. 6 minus 4 is 2. Okay, and then 5 minus 2 is 3, and half of 6 is 3, so that's 0. Again, we get a neutral charge, minus 2 plus 2 for the overall molecule, but definitely we'd have to say that this structure up here is actually the most stable. Okay, and so you do, in fact, have the least electronegative in the middle, even though you have another one of them as a terminal atom. That would be the most stable. Okay, let's look at NO3 minus. This is an ion. So you have 1 nitrogen with 5 valence electrons. And then you have just the additional electron for the negative charge there. That gives you 24. All right. So what are the possible ways to configure this? Again, if all else fails, you just kind of do a symmetrical configuration like that. Put electrons in between. Okay, create octet. So we have 6. We need 18 more. Okay, there we go. We have 24. This nitrogen does not, however, have an octet. So we have the right number. That means we don't want to erase any, but we want to rearrange some. It only needs one more pair. So you can pick one from any of the oxygens that you want. I'll go ahead and pick it from this one. Okay, and there we go. So we have a double bond there and singles bonds there. So you could have 3 resonance structures. I'll just go ahead and draw them. And they're all equal. They will all give you an equal result as far as formal charge, because all you're going to do is move the double bond around here. Okay, so let's just practice doing that. So I'll put the double bond down here this time. Okay, and let's see, we need 2 more there. Okay, so nitrogen has an octet, everyone else has an octet, and that's it. And again, we can move it over to this side right here. That won't change the formal charge. So the way, again, you could write that is with solid and dashed lines, where the dashed line represents 1/3 of a bond. So it could be a 1 1/3 bond, meaning this lone pair is delocalized. It moves all around here. Let's just go ahead and do that. I won't draw the 3rd double bond. I'll draw it like this. And I'll draw it like this in a dashed line here. Like that. And that's 1 1/3 bonds. This is 1 1/3 bonds. Again, go back to the instructional video if this isn't making sense to you. It's explanation of that. Except in that one, it was ozone. It was a half. It was 1 1/2. This one has 1 extra lone pair for 3 possible bonds, so it's going to be moving all around in there. And that's the way you would do that resonance structure there, okay? All right, SeO2, let's do this one like this. First of all, let's count electrons. And selenium is right there. It's below oxygen, so it also has 6. It's the 6th element from the left. And oxygen, there's 2 of those. Okay, let's do it like this. And let's do it like this. And let's get on screen. Okay, so let's, there you go. There's selenium oxide. Sorry about that. Okay, so that's where we are. So selenium has 6 from the periodic table. Oxygen also has 6 times 2 though. And so you have 18 electrons. And we're going to try these 2 configurations here. Okay, so let's see. I've got 16 there. So now I have to add 2 more. So I'm going to put those on the central atom. So now I have 18, but I don't have an octet around selenium. So again, I'm going to take one of the lone pair outside here and move it in here. Okay, and there we go. So now octet, 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 and you've used 8, and 8 is 16, and 2 more. If we had flipped it around and put the double bond over here, that would be acceptable. That would have been a 1.5 bond, so you could have shown that as 1.5 bonds there for that resonance structure. But this is totally different. This one's totally different over here. But the electron configuration is going to look the same. So let's go ahead and do that. Okay, there we go. So octet, octet, octet. All right, so let's do the formal charge on this one. 6 minus 6 lone pair minus half of 2 equals -1. So we already have a charge there. Selenium there is going to be, it has 6 valence electrons also, minus 2 lone pair, minus half of 1, 2, 3, 4, 5, 6. That's going to give it a +1 charge. And the oxygen on the right is 6 minus 1, 2, 3, 4 lone pair, minus half of 1, 2, 3, 4 bonding. And that's going to be 0. So everything charge balances there, that's fine, but you know, not quite the most stable possible. Okay, let's try this one, the O on the left. I'm always starting left to right, so when you see 2 O's here, it's going to be O on the left, O on the right, O in the center, and then SE. I do it from left to right. Okay, and that is going to be 6 minus lone pair here is 6, minus bonding is 2, so half of 2. Also -1. Okay. All right, and then the oxygen in the center. Okay, these aren't electrons, it's just a colon. Okay, is 6 minus 1, 2 lone pair minus half of 1, 2, 3, 4, 5, 6 bonding. That's going to equal +1. And then selenium down here is going to be 6 minus 1, 2, 3, 4, 6 minus half of the bonding, which is 1, 2, 3, 4, and that is going to be 2. So that's going to equal 0. Okay. Okay, so when we finish this, we end up with exactly the same formal charges, but on different atoms. So how do we deal with this? Which one's the more stable? Well, selenium, if you look at the periodic table of electronegativity, is actually the least electronegative, and therefore it should go in the middle. So this would be the more stable. There's another rule that I didn't mention in the instruction video, so let's mention it now, is that the most electronegative element, if there's a tie, then the most electronegative element should have the lowest possible charge. So oxygen is the most electronegative element. So here the oxygens have a net charge of 0 and -1. That's a net charge of -1. Here they offset each other, -1, positive, and that's a net charge of 0. So again, that's a new rule that wasn't in the instruction video. Because the oxygens here have a net charge that's more negative than the net charge they have here, that is when you add them together, that this one would be the more stable as well. Okay, so that takes care of this assignment. Again, we'll practice these more in the spring as we get closer to the AP exam. We'll practice them several times. But just kind of master this now. They're not that hard. They just take some practice, and there's a few little twists to them. All right, so we're going to start a new unit on Wednesday, and so get this done as quickly as possible. All right, we'll see you in class.